we have two traveling waves, y1 and y2. The waves look very similar to each other, except for the fact that there's a difference in the sign. Now you have one minus sign, you have the other positive sign, and they superimpose on each other. That means it's a technical term for waves meet each other. So if you have two continuous traveling waves meet each other, what's the resulting? You have to calculate what the resulting wave looks like and the properties of the resulting wave. So let's try and understand in general, how do we figure out what happens when two waves meet each other? So let's talk about superposition of waves. And the superposition of waves is given by a principle, and it's called as, wait for it, superposition principle. And the principle just says that if y1 is the equation for first wave, or equation for the displacement of wave number 1, and that could look like something like, a1 equals sine kx plus omega t. And if you have y2, which is another wave, which can be represented by a completely different equation, maybe it's k dash x plus omega dash t. And if these two guys were to meet each other accidentally or whatever, what's going to happen is the question. Well, the answer is the resulting wave, whatever results out of that, just becomes the summation of these two. And this is called as the superposition principle. Okay, it's a very simple principle. It doesn't just apply to waves, it applies to most of the stuff in physics. But anyways, now we're concentrating on waves. Okay, so we have been given a particular kind of waves that are superimposing on each other. The waves are of the form, you have y1 equals, let's say, a sine kx plus omega t, and you have the second wave has the same amplitude if you look in the question, and it's also a sine function. It has the same value of k, which means it has the same wavelength, and there's a minus sign, but with the same value of omega. That means it has the same frequency, which means it's also traveling with the same speed times t. The difference is the sign, and I'm pretty sure you now know what these signs tell you. This one is traveling along the negative x direction, right? Because the signs are the same, both are positive. So this guy is traveling along negative x direction, and this fellow is traveling along the positive x direction. So if you were to show this, you would have one wave this way traveling this way, if you call this as your positive x or something. And you have a second wave which has exactly the same wavelength, the same frequency, the same speed, but it's traveling in the opposite direction, and they're going to meet each other. And the question now is, what happens when they meet each other? Well, it's very difficult to get an intuition behind what's going to happen, but I think the best way to understand what's going to happen is use the superposition principle. Let's do that quickly. Our resulting wave y is going to be y1 plus y2. So that's going to be a sine kx plus omega t plus a sine kx minus omega t. Now this can be simplified. You can take a as the common factor and you can remove it outside, and what remains inside now is a sine of a plus b plus sine of a minus b. You have that form inside, and you should brush up on your trigonometric identities. If you have sine of a plus b plus sine of a minus b, this guy is sine a cos b plus cos a sine b. This guy is sine a cos b minus cos a sine b. So the cos a sine b's cancel out. And so what you end up now is 2 times sine a cos b. This is what you would end up with. Okay? So you would get the same thing. This is a and this is b. So a multiplied by 2 times sine kx cos omega t. There we have it. okay? And I can refine this a little bit. We can call this as 2a sine kx. I'm gonna put that thing inside the bracket, and outside I'm gonna write this as cos omega t, and that's what the resulting wave looks like. So let me put a box around it. This is the resulting wave. Notice it looks nothing like a traveling wave. You know why? Because a traveling wave should have the equation of the form which we have seen before. It should be some function of kx plus or minus omega t. That's what a traveling wave looks like. This is not a function of kx plus or minus omega t. You have a kx inside a sine function and you have an omega t inside a cos function. So this is of the form f of kx times g of omega t. Okay, because you have two different functions within which we have kx and omega t. And the question now is, if this is a traveling wave, this we have intuition behind that this is a wave that travels in space with respect to time. What does this do? What is this? Well, first things first. Let's try and get a feeling for what's going to happen over here. Notice that the kx and the omega t have now been separated. You have separate functions for them. And I'm going to write this a little differently so that you can identify this equation. I'm going to call this as the new a. I'm going to call this as r. Okay, so let me call this as r times cos omega t. Can you identify this equation? Have we seen this equation before? Isn't this of simple harmonic motion? That's right. This represents simple harmonic motion. That's not surprising. Every particle is doing a simple harmonic motion. Every particle is also doing a simple harmonic motion over here if this is a sine function, if this was sine. But what's different over here is, notice that every single particle is having the same phase. That's important. All particles, see y represents the displacement of the particles in the y direction, and every single particle has the same phase. So this tells you all particles are in phase. That's amazing. That's not what you find in a traveling wave. If you have a traveling wave which is moving this way, you would find this guy over here is ahead of this guy. So particle 1 is ahead of particle 2. In fact, particle 1 is 2 pi radians ahead of particle 2 because the wave hits here first. But that's not what we see over here. Every single particle should have the same phase because there is no phase difference at all. But notice every particle doesn't have the same value of amplitude. This represents the amplitude, right? R is the amplitude. And notice amplitude depends on the value of x. That means if you were to try and plot this over here, what would the plot look like? Well, I can only plot it at some value of time t. So let's say I take time t equal to 0. I'm going to plot this thing at time t equal to 0. Then this cos goes to 0. This cos becomes 1. I'm sorry, this becomes 1. And I have to plot y equals 2a sine kx. That's easy. That looks like this. That looks pretty much like this wave. Okay, and this now has an amplitude 2a minus 2a. Okay, but what's important is if I wait for some time, if I go for time t equal to something later, it's not 0. If I wait for some time, the wave doesn't shift towards the right. In fact, notice that there are some particles over here and here and here and here. At these particles, y is always equal to 0. Because for these particles, for some value of x, this whole function goes to 0. And if r is 0, notice y is always 0 regardless of what time you look at. In other words, these guys over here, these guys are always at rest. They don't oscillate, so they are at rest. And these guys are called as nodes. They don't oscillate. And on the other hand, look at these guys. These guys oscillate with maximum frequency, maximum amplitude. These guys are the ones that have the maximum value of r. For some value of x, r will be maximum. Okay. The value of x is that kx is pi by 2. okay, and kx is say 3 pi by 2, these guys will have maximum values. And even these guys, they're also given a name. So let me indicate them in black. So I'm gonna put black over here. Okay, these guys over here, they're also given a name, and they're called as antinodes because they have the maximum value of amplitude. Okay, that's maximum value of the amplitude R. And every single particle has their own amplitude. That's the speciality of this. All particles are in phase, but every particle has its own value of amplitude. This guy has an amplitude of 2a. These guys have amplitude 0. Okay, and all the other particles have intermediate amplitude in between. So the difference between a traveling wave, which is this form, and this wave is that this wave, every single particle are in phase with each other, and all particles don't have the same amplitude. So if you were to see an animation of this, look at the animation. I can't draw an animation, but I can try and give you some sense for this. If this is what it looks like at some time t equal to 0, a little later in time you would see the graph goes like this. This is how the same wave evolves. That's what it looks like. Notice that the particle has come down. This particle has gone here. This particle has gone here. This particle has gone here. And notice all these particles are doing it together. Okay, they will finish the same number of oscillations in a given time. And look at these particles, they're at rest, they're not moving. And even this particle has come down, and even this particle has come down, and even this particle has gone up. If I wait for some more time, okay, the wave is going to look like this. So I'm not drawing different waves, I'm drawing the same wave at different instance of time. And then a little later in time, the whole thing is gonna be flat. Okay, so the whole thing is gonna flat. And if I wait for a little more time, it's gonna go like this. And after some more time, it's gonna go like this. And then it's gonna go like this, and then it's gonna repeat. Ooh, look at this. This wave is not traveling at all. I mean, if there was a boat over here, for example, this boat, if I kept this boat at this point, that boat wouldn't rock at all. On the other hand, a boat over here would rock like crazy. If this was a water wave, for example. And that's the thing. And so we give names to these waves, and these are called as stationary waves. And they are characterized by nodes and antinodes. Okay? And important thing to notice is that between any two nodes, consecutive nodes, there's one antinode, and between any two consecutive antinodes, there must be one node. Okay? They're characterized by this, and these are some differences that you have between stationary waves and traveling waves. So now that we have some idea behind them, we're gonna work out we're gonna work out that problem in the next video. Okay? So stay tuned.